In this video, we will continue our introduction to data, and in particular, we will be looking at data basics. This is our overview slide, which I'll spend about 5 minutes going over before going over each topic in more detail and with more examples. We will start with the data matrix, which is a convenient and common way to organize data. We will be using Excel sheets as our data matrix. Next, we will go on to look at different types of data. There are two main types of data. The first is numerical variables, and the second is categorical variables. Numerical variables are simply numbers. So with these numbers, you can add them, you can subtract them, you can take the averages. Numerical variables break down into two other types. So numerical variables can be continuous or discrete. Continuous means the difference between two values can be arbitrarily small. An example I'm going to give you is age. You might consider people born in the same year the same age, or you might have differences by month. You might say, oh no, if you're half a month older, then you're not the same age. You can go by the date and say only the people with the same birthday have the same age, and then if you really want, you can go down to the hour, and if you're twins, I assure you there are many twins who will say they are the older twin because they were born minutes earlier. And if you want to get really extreme, you can try to go down to the second or microsecond. But the difference in age can differ by many different values, and you can go arbitrarily small down to the microsecond. Whereas discrete numerical values can only differ by fixed amounts. So an example will be family size. Family sizes will differ only by whole numbers because in general, the number of people in your family is a whole number. You don't have 3.2 people in your family. You either have 3 or 4 people. So again, there are continuous numerical variables and discrete numerical variables. Next, we have categorical variables. These represent categories. They are not numbers. The categories are called levels. So an example might be among high school students, you might have freshmen, sophomore, juniors, seniors. Or maybe among recipes, you might have desserts, entrees, appetizers. These again are categories. While you might try to classify or code the categorical values with numbers, so you might say freshmen are the number 1, and you might write down a number 2 when someone's a sophomore, a 3 when they're a junior, and a 4 as a senior, but they're not truly numbers. And adding the two numbers, like adding a freshman and a sophomore, would make no sense. So categorical means they're groups, they are not numbers inherently. Among the categorical variables, you can have ordinal variables. In other words, some categorical variables are ordinal variables, and those are categories that have a natural ordering. An example will be the last example of high school students. Generally, you think of freshmen as the lowest on the totem pole, then next comes sophomore, next comes juniors, next comes seniors. So there is sort of this natural ordering. It's not just an ordering that you decide, but it's something that everyone would sort of agree on. If you say, how should we order this? Everyone would agree freshmen are lower than seniors. Next, we will talk about relationship between variables. We can have associated variables or independent variables. Associated variables show some connection with one another, and among the associated variables, there can be a positive association or a negative association. A positive association means when one variable increases, the other also increases. A negative association means when one variable increases, the other variable tends to decrease. Independent variables are if two variables are not associated, they are said to be independent. There is no evident relationship between the two. So variables are either associated or independent, never both. To see relationship between variables, we often use scatter plots. So we will be looking at some scatter plots next. Next, we will look at explanatory versus response variables. So if one variable affects another, the variable driving the change is called the explanatory variable, and the variable that is affected is called the response variable. That is, the explanatory variable might affect the response variable. This does not mean there's a causal relationship. A formal evaluation is needed to verify causality, which brings us to this last point, which is causality versus association. So we'll discuss how you can have an association without causality. And actually, right in between, there's one more topic, observational studies and experiments. Researchers perform an observational study when they collect data in a way that does not directly interfere with how the data arises. That concludes our introduction slide. So now we can go back up to the top and take a closer look at the data matrix. As I mentioned in our overview slide, for our data matrices, we will be using spreadsheets. So this is our first example of a data matrix. This data matrix represents information about different loans. Each row over here represents a case or an observation. So here's information about one loan. Actually, let me start with the first loan here. This first loan, which I will highlight in yellow, this first row here of the spreadsheet represents the information of our first loan. This next row here represents information about a second loan. The row underneath represents information about a third loan. And we can keep going. I didn't fill in this spreadsheet all the way just because it would take too long. I also used an Excel trick to hide a bunch of rows 7 through 48, because your book has row 50 here is another loan. So again, each row represents a different case. Each column now represents the variables. So in other words, there are certain things we want to know about the loan. This first row here tells us what the variables are, what we're interested in. We're interested in the loan amount, and that's in the first column. So this column will show all the different loan amounts. Here for the first loan, the loan amount is $2,200. We have another loan for $6,000, another loan for $25,000, and all the way down to a loan for $15,000. The next variable we're interested in is in the second column. Here we have the title. It's called interest rate. This is the interest charged on the loan. This first loan has an interest rate of 10.9. The second loan, the $6,000 loan, has an interest rate of 9.92. This next column here is the term variable. It tells us how many months our loan should take to repay. So this first loan of $2,200 should take 60 months. The second loan of $6,000 should take 36 months. The grade represents the probability that the loan will be paid back. So here, this column, the first loan, has a pretty good chance of being paid back. So this $2,200 loan. Whereas here in the third loan, the $25,000 loan, the grade is quite low, E. It's a little more of a risky loan and may not be paid back. This next variable, this next column is state. This is the state the loan was taken out in, or where the borrower lives. So the $2,200 loan was taken out in New Jersey. The $6,000 loan was taken out in California. This column here shows the total income for the loan of the borrower. So here, the person who borrowed $2,200, their total yearly income is $59,000. And last, we have home ownership. This talks about whether or not the borrower owns their home, whether they rent, or if they own but have a mortgage. So this $25,000 loan, the person who took out the loan has a mortgage on their property. And just a quick note, in case you need to make a spreadsheet or a data matrix with Excel, there's some things in formatting here. You can highlight an entire row and you can designate the format as percentages. You can designate dollar amounts, and then you can just designate number amounts or dates. By clicking this arrow, you can get other things other than just dollar and percent. The other thing is, if you want to have more decimal places, you see here, my interest rate was 11% because it initially rounded up my 10.9 to 11. So what I did is I clicked this number here to show I want more decimal places. Here we'll give you fewer decimal places, right? It's going from 2 decimals to 0. Here we're going from 0 decimal places to 2. So you click this arrow if you want to show more decimal places. Click this arrow if you want to show fewer decimal places. Often there are longer explanations about each variable. Here we just kind of have short names for them. And here's the longer explanation for each variable, which you may look at. And we'll answer some questions. What is the grade of the first loan? So here's the first loan, and we can read along this row, and we see the grade is B. So let me write that in. What is the home ownership status of the borrower of the first loan? So we've already talked about that. They rent. So we'll answer that question. Our next example is the grade for assignments, quizzes, and exams in a course are often recorded in a grade book that takes the form of a data matrix. How might you organize grade data using a data matrix? Here, I've organized my data in an Excel sheet. I have my student name, assignment 1, 2, 3, 4, 5, quiz 1, 2, 3, 4, and exams 1 and 2. So each row represents one student's grades. So here we have Bilbo Baggins with his grades, Samwise Gamgee with his grades, Mary Brandybook, but I didn't actually put in grades, and Peregrine Took, which I did not put in grades. But you can see Bilbo Baggins has an 86 on his first assignment, 97 on his second assignment, 68 on his third assignment, 93 on his fourth assignment, 85 on his fifth assignment, a 99 on quiz 1, 90 on quiz 2, 80 on quiz 3, 78 on quiz 4, 92 on exam 1, and 90 on exam 2. You can see Samwise Gamgee has a 90 on quiz 1, 94 on quiz 2, 91 on quiz 3. The second example in our book is we considered data for 3,142 counties in the United States, which includes the county's name, the state where it resides, its population in 2017, and how its population changed from 2010 to 2017, poverty rate, and 6 additional characteristics. How might these data be organized in a data matrix? Before I turned the page in the book, I went ahead and made this spreadsheet. So the county was Santa Clara, state, California, population in 2017. I looked this up. Population changed, so I looked up the population in 2010. So the change was 1,046,000. The poverty rate was 68, and I didn't know what the other 6 variables were, so I just named them x1, x2, x3, x4, x5, x6. And then I turned the page and I realized they gave me the data. But anyway, let's just look at this data just for a moment. I just want to be able to look at this data and make some inferences. So population change from 2010 to 2017 is an increase, 1,046,000. If it had been negative, either I would have put a negative sign, put it in red, or sometimes spreadsheets put a parentheses around it. That's an accounting thing. Parentheses around a number means it's negative, but it's positive, which means it increased from 2010 to 2017, which means if I want the population in 2010, it's going to be 1,046,000 less than the population in 2017. So that is, I'm going to take my 1,932,000 and subtract the change, 146, and I get 1,786,000 for my population in 2010. Furthermore, if I want the percentage change, like how much did the population change between 2010 and 2017, that question is this change here, 146,000 is what percent of the original population, 1,786,000. And there's a little trick in probability. If I take this sentence, if I can write my statement, if I can write my problem in this way, the word is always, you can substitute equals. What, you can substitute an x, and then percent is just percent. Of, you can substitute a multiplication. So this sentence, if you can get to this sentence, then it's pretty easy to get to the equation. It's 146,000 equals X percent of means multiply, and then you have your second number. So this is the equation you have. To solve the equation, you're going to divide both sides by the 1.7 million, and you get 0.08, which converting to a percentage, you move the decimal over two places, and you get 8%. I wanted to do a few more examples of percentage problems. So I moved from our last slide, this here, the percentage changes. We were answering the question, 146,000 is what percent of 1,786,000? I substituted in my equation an equal sign for is, what I substituted in X, percent I kept the percent, and of I did a multiplication. So this was the equation that I wanted to solve, and here I resolved for percent by dividing 146,000 by 1,786,000, and I kept more decimals, so it's actually not just 8%, but it's 0.0817. Moving the decimal over two places, I get 8.17%. If the question had been worded this way for percentages, what is 8.17% of 1,786,000? Then what I would do is I would say what is an X, is an equals, 8.17. I'm just going to convert that by moving the decimal over two places to a decimal. The word of is a multiplication, and 1,786 with the 3 zeros. And that, when I calculate it, is going to be 145,916. It's essentially the same as here, except that when I did this percentage, X percentage here for 8.17, there were actually more decimals, so it should be a little bit bigger. But this is how you would solve this problem. With the 8.17%, it'll be 145,916. A similar type of problem, it could have been 146,000 is 8.17% of what number? Again, I would write my 146,000 is an equals. 8.17, I'm going to convert that to a decimal. Of is a multiplication times what number? And what number I'm going to say is X. So this means X is equal to 146,000 over 0.0817, and my answer is 1,787,025. Again, this answer is a little bit different from here because my 8.17 was rounded. Okay, so that's it for this little tip on how to work percentage problems. In your book, I hadn't noticed that it had data by county in this data matrix here. So when you turn the page, this is the data matrix for the county, including the name, the state where the county resides, its population in 2017, its population change from 2010 to 2017, poverty rate, and 6 additional characteristics. So here's the data matrix. Here's information about the variable. This first column here, that's not really a variable. This is what identifies the county. So here's the identifier for the record. This will tell us, this first row is information about Autauga County in Alabama. So the variables are the state, the population of the county, the population change between 2010 and 2017 in the county, the poverty rate, what percentage, and you can look up poverty, percentage of the population in poverty, home ownership, this also is a percentage. What percentage of this county owns their own home? What percentage of the living units are multi-unit? Multi-unit meaning a structure where many people can live. We're not talking about like a family, but many families can live. So that would be like an apartment complex, condominium. So 7.2% of the housing are multi-unit type of living conditions. So if you live in a multi-unit, a condo or an apartment, that a condo or apartment counts as a multi-unit. The unemployment rate, what percentage of the people, the workforce in this county are unemployed? Metro is a yes/no question, whether the county contains a metropolitan area. The median education, so here we have some college or a high school diploma. And last, we have the median household income. We are going to use this data matrix now to look at types of data. Our biggest division of data is whether or not it's numerical data or categorical data. And here I've kind of drawn that we can separate our data into numerical or categorical. If our data is numerical, that means the data is a number, and it makes sense to add, subtract, or take an average of these numbers. Categorical data, they represent categories or groups, and the categories are called levels. So you want to be careful, because sometimes categorical data, we might assign a number to it just so that we can do a shorthand. So for example, in our overview, we talked about classifying high school students as freshmen, sophomores, juniors, and seniors. So those are categories. It's a categorical variable, that classification. What class are you in? Freshman class, sophomore class, junior class, senior class. And we might actually, if we were writing it down, making a table and taking notes, we might say that freshmen, we might put a number 1 next to them, a 2 next to the sophomores, a 3 next to the juniors, and a 4 next to seniors. But that does not make it numerical data, because it would not make sense to add or subtract. You don't add a freshman and a sophomore and get a junior. So you might code categorical data with numbers, but they aren't truly numerical data because they don't really behave like numbers. Coming back to numerical data, we can divide up numerical data into 2 categories, continuous or discrete. Continuous data means that the difference between 2 points of data can be arbitrarily small, whereas discrete, the 2 numbers can differ only by fixed amount. So an example of continuous is if you want to talk about who's taller. Often 2 people who are really the same height stand next to each other, and each one tries to claim that they're taller. And really, they're not. They might both be 5 foot 2 inches. So that's one way. You're saying inches. That's our final way that we're going to divide height. But they might insist that they're half an inch, or maybe even a centimeter, maybe even a millimeter taller. So they can continue to get smaller and smaller differences and say that's what makes them taller. So that's continuous. Whereas discrete means you can only differ by a fixed amount. Our example in the overview was family size, because the people in your family, they're only whole numbers. You don't have half a person in your family. You want to be careful though. Discrete does not mean whole numbers. And an example of that is money. So how many dollars do you have? You could have $5.25. That means you have $5.25, right? So we write money as a decimal. However, money will be discrete because this last decimal here, the penny, is the smallest division you can get. You don't say that the amount of money you have, you can't say the difference between the amount of money I have and the amount of money you have is 0.001 or half a cent, 0.005. There's no division like that, because money comes, the smallest increment you can do for money is the penny. It doesn't get any smaller than that. So money is discrete, even though it is a decimal. Categorical data can be further divided into ordinal versus not ordinal. So an ordinal variable are categories that have a natural ordering. And the example of that is the high school students. They can be freshmen, sophomore, junior, seniors, and naturally you'd think of freshmen as lower on the totem pole than sophomores, juniors, and seniors. There's a natural order to that. we're going to use our types of data, this little chart here that we had on the previous slide, and we're going to apply it to this table that was even earlier in the video. This is our county data. If you need a bigger table, if this is too small on your screen, go back a little bit in the video, screenshot it when this table was bigger, or take a look in your book because this table is straight out of your book. So we'll look at the different variables. Again, this name here just identifies the county. It is not a variable. But we'll start with the variable state. So over here, how do we divide up data? Numerical versus categorical. Well, this is certainly not a number. So it is a categorical data. Is it ordinal or not ordinal? Well, you can try to put an order to the states by alphabetic order, I suppose, or you could try to put an order to the states, but I could say maybe we should order the states by population. Someone else might say maybe we should order the states by the order that they joined the United States. So there are different ways you can order it. There's no natural ordering that everyone would agree, yes, that makes sense. So it is not categorical. Oh, and last, so categorical, not ordinal. Next we'll go to population. Is it a number? Is it a category? Well, it's definitely a number. So is it continuous? Is it discrete? So population, that's a number of people. You're not going to have half a person. So this is going to be discrete. Numerical, discrete. Population change. So this is percentage change in the population. So this is important. If it weren't percentage, but just the straight up change in population, that would be, one, it would be numerical, it would be a number, and it would be discrete because you don't change by half a person. However, because this is a percentage change, percentages are always continuous because it's a number divided by a number. You can get fractions, you can get decimals, and they can be very small. So population change is numeric and continuous. Poverty level, over here, poverty is also percentage. As I said, it's a number. Poverty is a number. Clearly, you can see it's a number. And it will also be continuous because it is a percentage. Home ownership, another percentage. So that's going to be numerical continuous. Multi-unit, again, a percentage. It's going to be numerical continuous. Unemployment rate, another percentage. That's going to be numerical continuous. Metro is a yes, no, so it's not numerical, it's categorical. Is it ordinal? Is there an order between yes and no? Well, not really. I mean, you always say yes first, but there's nothing natural about saying yes first. It's just that you're conditioned that way. So it's categorical, it's non-ordinal. And then we have median education. So clearly this is not numerical, it's categorical. Is it ordinal or not ordinal? Is there an order, a natural order to some saying that you have some college versus a high school diploma versus, let's say, you had college? Well, generally you think of high school diploma as coming before some college, so you would say yes, this is ordinal. Last, median household income. It's numerical. It's obviously a number. It makes sense. You can add the numbers together. What is our combined income, right? You would add them together. And then is it continuous versus discrete? Remember, we talked about money. It's going to be discrete because your household income, your income and my income, they're not going to differ by more than a penny. And here they're only showing dollars anyway. So numerical and discrete. Our next question about types of data. Data were collected about students in a statistics course. 3 variables were recorded for each student: number of siblings, student height, and whether the student had previously taken statistics. I'm not sure why height was interesting, but whatever. Classify each of the variables as continuous numerical, discrete numerical, or categorical. So number of siblings. Well, that definitely is a number, so it's numerical. And in general, number of siblings is going to differ by a whole number because they're people, so these are discrete. Student height, again, that's a number. And then I will say this is continuous because You know how when two people stand next to each other and they argue over who's taller, they're talking about sometimes, and they really do look the same height. So at that point, they're measuring how fluffy their hair is on top. They're looking at microcentimeters. So you can really get down, if you want, to a very small, difference, arbitrarily small, till it's ridiculous. How about previous statistics? Have you had previously had statistics? That sounds like a yes/no question. That seems like categorical, and it is not on. It is not ordinal. Our next example of types of data, an experiment, is evaluating the effectiveness of a new drug in treating migraines. A group variable is used to indicate the experiment group for each patient, treatment or control. So we have a variable called group, and it tells you whether the patient is in treatment or control. The number of migraines variable represents the number of migraines the patient experienced during a 3-month period. Classify each variable as either numerical or categorical. So group, as we said, the groups are treatment or control. Those are not numbers. It's categorical. It is not ordinal because there's nothing about one group being more than or less than or ordered. The number of migraines, that's definitely a number. And unless people can get half a migraine, but I don't think they can. I think either you have one or you don't. So we're going to say it's discrete. So again, either you have a migraine at a particular time or you don't, but you can count the number of migraines you've had, so it is numerical. Next, we're going to talk about relationship between variables because some variables are associated or they seem to have connection with each other. Other variables do not seem to have any connection, and we call those independent variables. So if two variables are not associated, they're said to be independent. There's no evident relation or connection between the two. So variables are either associated or independent. When they're associated, they can be positively associated, which means when one variable increases, the other increases, or negatively associated, meaning when one variable increases, the other decreases. So let's take a closer look at that. I moved our notes about relationships between variables over here for your reference. And then the next note is that scatter plots are useful to see associations. Here is the first scatter plot we will look at. It comes from our county data, and it's looking at two variables. The first one is percentage of units that are multi-unit over here, and I see that variable being studied because this is on the x-axis here, percentage of units. And then the next variable is home ownership rate. Maybe I should underline, let me use green. Home ownership rate. So that's this variable here. And what happened is I think there were hundreds or 3,142 counties studied. So what they did is for each county, so let's take a look at this first county. There's Atuga, which is in Alabama. We plotted on the x-axis multi-units, the percentage of multi-units. That's 7.2. So this is 20, this is 10. Somewhere over here is 7.2 on the x-axis, and home ownership is 77.5. So this is 80, somewhere here is 70. Somewhere over here at 7%. So I said this was 10. So somewhere over here is about 7.2%. And I better write this in a different color. So again, I'm going to be plotting this number versus this number. This is 7% here. Somewhere in here is 77%. So we get a number, a dot here. So this blue dot, approximately, because I'm not being super exact, but this represents these two numbers for Atuga County. It's getting a little messy over here. So I'm going to remove those 2 points for Atuga County just so we can see what we're doing next. Your book has chosen this point. Somewhere there's some county, and I think your book tells you which county, but there's some county where the percentage of units in multi-unit structures is a little under 40%, and the home ownership is somewhere roughly at 30%. Let me do one other point that I can see from this table here. Let's do the last one, the Cherokee. So here we have something, multi-unit structures represents 4.3%. Oh, you know what? This one's also another 70%. Let me go for something different. Here we have, in this county, Blute, 3.7% multi-unit, 82% home ownership. So 3.7, wow, that's really small. Over here, somewhere over here, this line represents 3.7% of multi-unit structures versus the 82% in home ownership. So that's a little above 80. So somewhere around this blue dot represents the data for Blute, Alabama, the relationship between multi-unit and home ownership variables. Notes from our book, each point in the scatter plot, so here's each point, and there's like 4,000 of them, because there's, 3,142 points, represents a single county. For instance, the highlighted that corresponds to county 413, that's this yellow one we had talked about. There's approximately, we said a little under 40%, it's 39.4% of units and multi-unit structures. At the home ownership rate, we said was about 30%, it's 31.3%. So this scatter plot, it kind of seems, if I were to draw a line to represent the trend of this plot, kind of through the middle of all the points, it would sort of go downwards. So what this represents to me is county with a higher rate of multi-units, that's over here, right? The percentage goes higher, but they tend to have lower home ownership rates, right? So counties with a higher multi-unit tend to have lower home ownership rate because there's a downward trend. You can see this in the line. These variables are said to be negatively associated. The scatter diagram does not tell us why this relationship exists, but we can investigate those ideas to determine which are the most reasonable explanation. But again, the diagram doesn't explain, it just says there's a negative association between multi-unit dwellings and home ownership rates. Here is another scatter plot from your book. It examines the relationship between counties' population change from 2010 to 2017, and we know that because this axis, the y-axis, is about population change over those 7 years, and the median household income, and that is represented here on this axis. Are the variables associated? So in other words, is there a general trend? And like I did for the other scatter diagram, if I tried to draw a line sort of in the middle of all the dots, there is this sort of upward trend. The other thing I can do to look at trends is I can try to draw a little oval that encapsulates most of the points. And you can see the oval also tends to point upwards. So if you don't like drawing the line, you can draw the oval to kind of encapsulate most of the points. And here you see there is this upward trend. In other words, there's a weak positive, upwards is positive association and the relationship between median household income and population change. Counties with higher median household incomes, though that's looking at household incomes over here. As we go up in the household incomes, then the rates of population change also goes up, right? So here you have a low household income, and you see, for example, at this point, you have a number that's sort of low in population change. Whereas if you come over here at a higher household income, let's say 80,000, you see that the numbers tend to be a little bit higher than over here. Like, I don't know, the middle number might be here. But you can see when you compare for higher household incomes, you have higher population changes. I wanted to show you some other scattered diagrams just to get the idea a little more clear. And this is from the book called Statistics. It's a book by Freeman, Pisani, and Purvis, and I'm very fond of this book. These two illustrations show us scatter diagrams, and it also talks to us about a correlation coefficient, which your book does not introduce, but I think it's very useful. In the statistics book, they talk about how to calculate it. They go into some mathematical detail, which I am not going to do, but what I am going to tell you is this correlation coefficient. The correlation coefficient is a number that goes between -1 and 1, and it gives you a measure of how associated or how correlated your data is. So I have this number line here. It goes between -1 and 1, and in the middle, right in the middle between -1 and 1 is 0. When the correlation coefficient is 0, there's no association. As you go towards 1, you get more and more positive association, where 1 is perfect positive association. It's a perfect line. As you go from 0 to -1, you get more and more correlation, but in the negative direction. So -1 is perfect negative association. So we'll take a closer look at each of these images. Here we have an example where the correlation coefficient is 0. Remember, correlation coefficient means no association. And if we try to draw some circle around the main parts of the data, we get something that looks more like a circle, not so much an oval around a line, not even trying to form a line. Here we have correlation coefficient is 0.4. Remember, as we go from 0 to 1, it's more of a positive association. Looks a little tighter, like the oval might be something like this, which looks a little tighter. Here's a correlation coefficient 0.6, 0.8. It's getting even tighter around a line, right? And it's definitely a line pointing upwards, where the data associated with higher x values, so let's say like x value, let's compare x value of 2. So the data for x value here, where data for x value of 5, it looks like it's maybe these points. So you can see the higher values of x tend to have higher values of y. This is lower values of x. They tend to be lower than the higher values of x. So this is why we say it's a positive correlation. And here we're getting to 0.9, and here it's 0.95. So you can definitely see the line. The oval is very tight, and as you move to the x-axis, higher values in the x-axis has higher values in the y-axis. Now we have our examples of negative correlation. Here we have a negative 0.03, so we're going from 0 to 1, 0.03. It's still not a strong association, but maybe a little bit of an association, sort of not quite a tight oval, but also not quite a circle. 0.5, it's a little bit tighter, 0.7, negative 0.9. Here we can see at negative 0.9, we're getting close to -1, and you can see the oval's tighter around a line. You can also see the association is negative. In other words, let's look at some low values of x, and the low values of x tend to be these points here for y, and if we look at the higher values of x, like 5, their y values, it tends to be this point here. So as we increase x, y seems to be smaller. Here's when x is low valued, but we have high values of y. Here's where x value is high, low values of y. That's the negative association. And then we continue on, correlation coefficient of 0.95, it's getting quite tight around the line, and at 0.99, the correlation is almost perfectly aligned, like really tight oval. So this would be our example of a strong association, strong correlation. This is weak association. Now that we've talked about data matrices, types of data, and relationship between variables, and also looked at scatter plots, we have a few quick other topics to go through. We'll start with explanatory and response variables. That says if one variable affects another variable, then the variable driving the change is called the explanatory variable, and the variable that is affected is called the response variable. That is, the explanatory variable might affect the response variable. And just a warning, to determine if this is really a causal relationship, if the explanatory variable really does affect a change in the response variable, we have to have a formal evaluation to verify causality, not just association. I've moved those notes about explanatory and response variables here for your reference so we can do a couple of examples. If there is an increase in median household income in the county, does this drive an increase in its population? In this question, what we're asking is if median household income might show an increase in population. So median household income is the explanatory variable. Population change, then, an increase in population, that would be the response variable. The next thing we want to talk about is observational studies and experiments. Researchers perform an observational study when they collect data in a way that does not directly interfere with how the data arises. In other words, we're just observing. We're not actually giving people treatments or somehow affecting the outcome. We're just observing. And some examples, researchers may collect information via surveys or review medical or company records or follow a cohort of many similar individuals to form a hypothesis about why certain diseases might develop. In each of these situations, when we're collecting information from surveys or reviewing records or then asking people, a group of individuals, to fill out something, researchers merely observe the data that arises. In general, observation studies can provide evidence of a naturally occurring association between variables, but they cannot themselves show a causal connection. In other words, we can't say something causes something else. When researchers do want to investigate the possibility of a causal connection, they conduct an experiment. Usually, there'll be an explanatory and response variable. For instance, we may suspect administering a drug will reduce mortality in heart attack patients. To check if there's really a causal connection between the explanatory variable, in this case, the variable is drug treatment. So drug treatment versus no drug treatment. And the response variable will be the mortality rate. So they will do, researchers will collect a sample of individuals and split them into treatment and control groups. And when the individuals are assigned randomly to a group, the experiment is called a randomized experiment. And the last thing we want to talk about is causation versus association. So we might find an association between two variables, but that does not always imply causality. And this is the example I'll give you. We might have a data set taken from elementary school students. So variables might include shoe size and math ability. I'm not sure why you would have a data set like that, but let's just say you're taking a data set and you have lots of variables, and two of the variables happen to be shoe size and math ability. So we might notice, someone might say, look, shoe size is correlated with math ability. But of course, we know that a bigger shoe size does not cause better mathematical ability. But for young children, shoe size is often an indicator of age, which also is an indicator of how much school or what grade they're in which case it would not be surprising that older children are better at math just because they've covered more math subjects, they've been in math longer, they're at a higher grade level. In this way, there might be an association between shoe size and math ability among elementary school students, but there's no causality. That is, shoe size does not cause one to be better at math. To review what we have covered in this video, first we talked about data matrices, a convenient and common way to organize data, and we used spreadsheets to do that. We said that in a spreadsheet, each row represents a different case or a different person or a different county, a different subject. And the variables represented, or the columns represented the different variables that we're keeping track of. That might be age, it might be grades, it might be population, whatever variables we're keeping track of. We talked about different types of data. Data can be broken up into numerical variables and categorical variables. Numerical variables are numbers, and it would make sense in numerical variables to add them, to subtract them, take averages. We can then further divide numerical variables into continuous and discrete. Continuous numerical variables means the difference between two values can be arbitrarily small. You can keep defining smaller and smaller differences, whereas discrete, these are numbers that can differ only by fixed amounts. Maybe, for example, family size, you can only differentiate them by whole numbers. In other words, you can talk about a family size of 3 or 4, but you can't get smaller. You can't get something in between 3 and 4 because you don't have 3.5 family members. The other warning I gave you is discrete does not mean whole numbers. So for example, when you're talking about money, how much money I have versus how much money you have, the difference in the amount of money we have, the smallest amount we can differ by is by a penny. We cannot get any smaller. So money would be an example of a decimal, but it's discrete. The other type of data, again, is categorical. So categorical represents categories or groups, and the example we had was high school students that can be represented as freshmen, sophomore, juniors, and seniors. And remember, we can code the categorical variable as a number. We can code freshmen as a 1. We can code sophomores as a 2, but they're really not inherently numbers, and it wouldn't make sense to add them. In other words, we can't add a freshman and a sophomore and get 3, which is a junior. So categorical variables, they are not numbers. They represent categories or groups, and some categorical variables can be ordinal. In other words, they have a natural ordering, such as our freshmen, sophomore, junior, seniors. The freshmen are considered lower on the totem pole than sophomores, juniors, seniors. Next, we talked about relationships between variables. So we can have associated variables and we can have independent variables. Associated variables show some connection with each other. And a positive association means when one variable increases, the other increases with it. A negative association means when one variable increases, the other decreases. If our variable is not associated, if variables are not associated, we call them independent. That means they're not associated, they're independent, there's no relationship or connection between the two. So variables are either associated or independent, never both. We also looked at several scatter plots that are useful to see associations and categorize them as positive or negative. And I also added some information about correlation variables. Last, we talked about explanatory versus response variables. If one variable affects another, the variable driving the change is explanatory, and the variable that is affected is response. We talked about observational studies. Researchers perform an observational study when they collect data, but they don't actually interfere with how the data arises. In other words, they don't try to do treatment, they don't try to intervene to make a result. And finally, we talked about causation versus association. Variables can be associated. In other words, they seem to go together, but it doesn't necessarily mean one variable causes the change in the other. And the example we had with that was shoe size and math ability. So that's it for this video. Thank you for watching.